Welcome to A Walk in the Park. Our goal for this exercise is for you to understand what a motion diagram is. And we have this very unusual family visiting the park, and we'll look at their motions to get an idea of how to create motion diagrams using some data. Next, we'll take the motion diagram data and we'll find that we can convert that quite easily into what we call a position versus time motion graph. As it turns out, you'll see that we'll be able to go back and forth between the two. Given a graph, I can find the diagram and vice versa. Once you've done the analysis on the graph, you'll find that you should be able to answer 13 key questions related to position versus time graphs. And these are key concepts for this unit that you will be quizzed on. So let's take a look at our little family. First of all, we have the father strolling along the sidewalk. And it says we're moving at a constant pace of 1 meter each second. And so here he is down at the bottom here. And we've actually drawn his first point in here. And I will label that with a time 0 just so we can keep track of which point is which. Now remember, what we're going to do here is create a motion diagram. And a motion diagram is essentially taking photographs equally spaced in time and laying them on top of each other. We have to have equal spacing in time to have a motion diagram. Our time interval that we're going to use here is very simple. We'll use a 1 second time interval is what we're going to pretend we're going to have here. And so that's what you see here. Each second will take one photograph, and during each time frame he'll move 1 meter along the sidewalk. So let's draw those first. So after 1 second he's moved over right here. I'll try to draw a nice diamond here with my pen. Colored in if you like. And I'm going to call this T1. Remember, this diamond that we drew over here is called T0. After 1 more second, he'll be over at 2 meters. That's time 2. After 1 more second, he's at time 3. After 1 more second, he's here. And we'll go for 5 total seconds from the start. So here's time 5. Now that we have that information, let's go ahead and create a graph of this. So here are a couple of pieces of graph paper for us to use. And what we have is one using the x coordinate system and one using the y, and both of them are versus time. So we have on our vertical axes, we have our distance units, or our positions, and on the horizontal axes in both cases we have time. Both of these are examples of position versus time graphs. The one on the left is your x position versus time. The one on the right is your y position versus time. So anything that moves in the x direction will graph on the left side here, and anything that moves in the y direction will use this graph on the right. On any graph, of course, you should give it a title and you should label the axes. I've already started to label the axes for you. So for our time units, we'll use MKS units of seconds, and for our position units, we'll use MKS units of meters. I'm just going to write a couple of labels if I can along these sides here. On this axis I have position, and on my horizontal axis it's time. So let's go ahead and graph our data. On the previous page we saw that the man started out at 0 meters at time 0. So I'm going to just create and if you don't mind, I'll use dots instead of diamonds for all of these. So the man has a starting point of 0, 0. At 1 second later he moved 1 meter along the path. 1 more second later he moved 1 more meter. Another second later he moved another meter. He was at 3 meters. At the 4th second he moved 1 more meter. And at the 5th second he moved 1 more meter. And you'll notice that these data points are linear. Now let's take a look at our second family member. Now we have a young girl riding on a bicycle. She's on the right side of the screen, and she's moving along at a good pace, a constant pace of 2 meters each second. She is starting at 10 meters. Each second she's moving to the left. I'll just draw a little arrow here. She's moving to the left, and so after 1 second she's got to move 2 meters, and she should be right here after 1 second. Alright, so now we're at 8 meters. Another second later, she should move over 2 more meters to the left, and so I'll put her right here for our second. 2 seconds later, she's going to move 2 more meters to the left. 2 more seconds later, she's moving 2 more meters to the left, and now she just ran over her little brother Stuart Little. 2 more seconds later, she'll move right over here, and here she is at time 5. Let's graph this motion, see what this looks like. All right, as you recall, the young girl started at 10 meters. So at time 0, she was up here at 10 meters. And once again, I'm just going to use big fat dots. Here she is at 1 second. She moved backwards 2 meters, and she was down at 8 meters. And so now she's right here. After 1 more second, she moved 2 more meters to the left, and now she was at 6 meters. After 1 more second, at time 3, well, I say backwards, but she was actually moving forward just in the negative direction, moving downward on our x-axis over on this left side. And if we look at time 4, she moved back 2 more meters along the x-axis. Our sidewalk is the x-axis. And at time 5, she'd reached the other side of the sidewalk, which is the 0 point on our x-axis. And once again, we see that her constant pedaling at 2 meters per second created another linear function. Isn't that interesting? All right, let's see who we have next. Our next family member is the apple who climbed the tree, and our apple, little brother apple, is going to drop out of the tree. And of course, as this apple drops, he will go faster and faster and faster until he reaches the ground, starting out at a slow speed and ending up at a fast speed. And so we're going to have to sort of guesstimate where he'll be. Later on, you'll see how to accurately correct for this. And so let's go ahead and start. Here he is up here. As you can see, I started him right at the top here. This is at time 0. And at time 1, let's just move him down a tiny little bit to show that he's going quick, very slowly. All right, here's time 1. For the next time instant, I'm going to maybe move down a little bit further, maybe about right here. Call that time 2. The next time instant, I'm going to go a little bit further, maybe about right here. Here's time 3. The next time instant, I'm going to go a little bit further. Let's call it right here. Here's time 4. And the last time instant, let's say he's all the way to the ground. And let's say this is at time 5. All right. Certainly, he's speeding up here. Over the first second, he's moved this far. Over the second, he's moved this far. Third second, he's moved this far. The fourth second, he's moved this far. And the fifth second, he's moved this far. Let's just write down the values that he's at in each case. At time 0, he's at 10 meters. At time 1, he's at, let's call this, I don't know, 9.75 meters. Remember, I'm just guesstimating, making these things up. At time 2, let's just say he's at 9 meters. All right. At time 3, let's say he's at 7.5 meters. All right. At time 4, let's say that he's at, let's call this 5 meters. And at time 5, let's see, he gets down to 0. Hits the ground. And so let's go to our other graph, our motion graph, and let's graph out his motion. So for the apple, we're not actually moving in the x direction. We're actually moving the y direction. So let's use that graph. And once again, let's label some axes first. Our units in the y direction are in meters again, and our time units are in seconds again. And if we label the axes here, this is our position, comma y, I call it y, and the one over here is we can call that our x position. And on the bottom scale, we have, of course, time. So here we are with our time axis moving to the right, and our position, larger values upward. And on our scale, it's the same scale we have to the left. That's 0. Across here, we have 10. All right, and we're going by ones. And our time scale, we start at 0, and we're going every other space by 2s. So our apple started at time 0 at 10 meters above the ground. So let's just draw a dot here. After 1 second, we estimated that maybe it dropped 1/4 of a meter. After another second, it dropped, we estimated, maybe down 3/4 of a meter down to 9 meters. And then after another second, we dropped, what did we say, to 7.5. So 7.5 is about right here. After another second, we said it dropped down to about 5 meters, which is about here. Let's say it went a little bit further. Just a little bit pattern, if we go a little bit deeper. And then finally, we said, all right, it was really speeding up now, and it made it all the way to the ground in the last second. And if you take a look at our shape here, we've got a nice curve going on here. It looks something like this. Let's draw a dotted line in through the curve. And here's our curve. All right. So unlike these other two cases, we had a linear function here. This is linear. This function is also linear. But this is some type of curve. So let's take a look at the little brother of family, and that of course is Stuart Little. Stuart Little's on his skateboard, and it says he slows down to a stop on a skateboard, and he's starting fast at first and slowing down to a stop. Alright, so here he is at 2 meters at the start, and let's just say that initially, let's just say that he goes 3 meters over the first second. Alright, so here he is after the first second, it's about right there. So this is at time 1. And of course, this is time 0 over here. At time 2, let's just say, let's make this easy numbers. Let's say he drops down to, he goes 2 meters in the next second. That's time 2. Let's say he goes 1 meter over the next second. Here's time 3. And then let's say he goes a half a meter over the next second. Here's time 4. And let's say he stops at time 4. All right. So at time 5, where would he be? Well, at time 5, he'd be right on the same spot. So to show that I'm on the same spot, I'll just circle it, and I'll put another label right next to it. That's time 5. So if he's sitting still at one spot for multiple time frames, you can add additional circles if you needed to. All right, let's graph this motion. So let's see, Stuart Little, at time 0, he started out at 2 meters. So here we are on our x graph, because he's moving in the x direction, not the y direction. I'll use an x graph for this guy. So at 2 meters, at time 0, he's at 2 meters on our sidewalk. Our sidewalk is our x-axis, using that as a reference. Even though he's somewhere further away in the park, we're using that as the reference. Then we said he traveled 3 more meters in the next second. He's moving to the right. So he's moving in the positive x direction. He's moving up along the x-axis, but he's moving to the right in time. And so what we're going to do is move him 1, 2, 3 meters. After 1 second, he's traveled 3 more meters. After the next second, now we're at 2 seconds, he's moved 2 more meters, we said. After 1 more second, we decided he's going to move 1 meter. After 1 more second has passed, he's moved a half a meter. And finally, we said he stopped here. And so for the next second, he hasn't moved at all. So he's still stuck over, it looks like at 8.5 meters on our x-axis. All right. So what we get is another curve. So here's our nice curve here. He's slowing down, slowing down, slowing down. And then for the last step of this, he's stopped. All right. Let's take a look at our final family member. So here's our puppy, Fido, and our little puppy is just sitting in the middle watching everything else happen as he enjoys the sun. And so at time 0, he's sitting right here. So I'll label this time 0. And sorry, I couldn't find a hot pink pen color, so we're going to use red again, but we're going to use not dots, we'll actually use hearts. And so at time 0, he's sitting right here in the middle at 5 meters. At time 1, what has he done? Well, nothing. He's still at 5 meters. And like we did over here when Stuart Little stopped for the last time interval, we just circled the previous one to show that he's still there. So I'm just going to draw another heart around that. And there's also is time 1. Time 2, he's still going to be staying there. So we can draw another heart around that one to show that he's at the same spot. So at time 2, he's also sitting there. Time 3, he's still sitting in the same spot, still chewing on that bone, watching people go by. So at time 3, he's still there. At time 4, he's still sitting there, enjoying himself. And at time 5, he's not going anywhere. He's just stayed there the whole time. So he's just loving it in the middle of the park. So let's go ahead and plot this motion. So at time 0, our little puppy Fido is over at 5 meters. He's just sitting there fat, dumb, and happy, just enjoying his bone and watching his family ride around the park. At time 1, he's still right where he was before. And you notice he's also, at time 1, somebody else is at 5 meters. So he's just crossed paths with his little buddy, Stuart Little. At time 2, he's still sitting at 5 meters. Now, at time 2, who's the closest person to him? Well, it looks like the little girl on the bike is at 6 meters away, so she's a meter away from him. Stuart Little's moving away from him. He's at 2 meters away from him now, and the man is getting a little bit closer to him. At time 3, he's still sitting there at 5 meters. He's not moving, and you notice we're getting a nice pattern here. And now the girl is still close to him. She's a meter on the other side of him. She's down at 4 meters now. She was at 6 meters. So she's a meter on the other side of him, to the left of him. And the man is still approaching. At time 4, the man is getting even closer. He's only 4 meters. He's at the 4 meter mark on the sidewalk, and the dog is still at the 5 meters. And finally, at time 5, Stuart Little is still sitting at the same spot at 5 meters along the sidewalk, and the man has also reached that same point at 5 meters. So we call this a constant function. All right, but it is linear. So constant function is an example of a linear function. Taking a look at our shapes then, we have 3 linear functions, one representing a stopped object, and as it turns out that slope is 0. And we can take a look at the slopes of the other 2 and see if there's anything interesting about that. So let's take a look at the slope for the man. And I'm just going to pick 2 of these points. I'm going to draw a slope triangle. All right, here's our slope triangle. And here's our rise. And here's our run, just using some math terminology here. And to calculate slope, and you need to write this work exactly as I write it, and this will help you understand exactly what the physical meaning here. We have slope in math as m, and of course in math we would say it's rise over run, or in math you would also say it's delta y over delta x. Now I'm going to put this in quotes here, because in reality here we don't have y's and x's on this graph. Instead, our y value, our vertical axis is using x's. So we're going to use delta x for our rise variable. Our run variable is right here on the horizontal axis is time. So we have delta x over delta t. That you should recognize from your reading out of chapter 2.1. This is the definition, or 3.2 actually, for your average velocity. Delta x over delta t is displacement over time. Changing the position over time is displacement over time. We have our average velocity, as it turns out. Well, let's take a look at the units of this as well. Well, the units for x are in meters, as we saw up above here. Here's our units for x. And our units for the y-axis, or our horizontal axis, right here, are in seconds. And sure enough, look at our units here. We're doing a little bit of dimensional analysis using this graph, and we can see that our units are in meters per second, which sure enough, those are velocity units. All right, let's go ahead and plug in the numbers here. So our slope is rise over run. Our rise here, we've got, it's rising plus 1 meter. So I've got plus 1 meter. All over, our run is positive 1 seconds. I'll do this very difficult math here. We've got plus 1 meters per second. That's the slope of this curve. Our slope equals plus 1 meters per second, which is our average velocity. So, and you look at this, sure enough, our slope of this line is a positive 1, and that turns out to be the velocity of the man. He was moving at 1 meter each second, positive 1 meter per second. So our big idea here on these graphs is that the slope of a position versus time graph gives us the velocity. All right. Now we're taking the slope over a time interval, over a 1 second interval here. Of course, I could have used the entire time interval here as well, and I would have gotten the same slope, 5 seconds and 5 meters. But the big idea is that slope on a position versus time graph gives us our velocity. Let's do the same for the girl. So for the girl, let's take these 2 points over here. And so here's our rise is actually a drop, so it's negative 2 meter drop. And our run, once again, is positive 1 second. So let me just show my work again, and this is the work you need to show. Slope equals rise over run equals, and my rise is right here, it's negative 2 meters all over positive 1 seconds, and we get negative 2 meters per second. And that's the velocity at which this girl is going. It's a constant velocity, which said she's moving to the left at 2 meters each second. So there you go. The left gives us, and remember what a velocity is. It's a direction and it's a speed. And our slope gives you just that. The speed is given by the magnitude of this. So here's our 2 meters per second is the speed. There's our speed. And the sign, which is right here, gives us our direction. All right, so we've got speed and direction. Gives us 2 components of velocity. Same thing down over here. We had our positive sign showing we're going to the right, and our magnitude is 1 meter per second speed. All right, so here's a velocity, and plus 1 meters per second. The plus telling us we're moving to the right, the 1 meters per second telling us how fast. And of course, for our little puppy Fido, he was moving, our slope is 0, and so his velocity is 0 meters per second. He's not moving at all. So the question for the curve is, well, what's the slope of a curve? We've got a little problem here because a curve has no particular slope. It has a changing slope. So you really have to take a look at the slope at various points along the curve, or you could take and maybe look at an average slope along the entire curve. So for example, the average slope along the entire curve, I could go from here, see if I can hit my target over the other side here. From here over to here would be an average slope of the entire curve. And I could use my rise over run on this entire slope triangle here and determine what the average slope for the entire path for this is. Or I could take any one of these points and say, all right, what's the slope at this point in the middle here? Well, the slope isn't this, and the slope isn't that. It's somewhere between. It's along here. And of course, it'd be nice if I had a ruler I could use. What we could do is we could take a ruler and sort of balance it on this curve. And when we balance it on there so it's evenly spaced on the left and the right side of this point, we could draw on a line and then draw a slope triangle around it. And use this slope triangle. We have a rise of plus 2 meters and a run of plus 1 seconds right here. And so it looks like at this point right here I have a plus 2 meter per second slope, which is our velocity. And that's the velocity at that exact point in time. All right, if we use a tangent to the curve. Going from one point to another over this broader time frame would give us the total distance we traveled over that time frame, which is right here. How many meters? We're going from 2 meters over to 8.5, and that's a gain of plus 4.5 meters. That's our rise. And our run here is positive 5 seconds. All right, so here's our rise and our run. So the slope of this entire line going from our initial point to our final point would give us, our rise is plus 4.5 meters over our run of plus 5 seconds. So we get 4.5 over 5, which is 0.9 meters per second positive, if you did that on your calculator. So that's our average velocity over that entire 5-second interval. I'll say from 0 to 5, times 0 to 5. So just as before, we've got the slope equals the velocity again, and we're doing it over a long time interval, so that gives us the average slope over that long interval, which gives us our average velocity, just like we had before. This is delta x, this is delta x, and over here we have our delta t. Delta x over delta t is average velocity. You could do the same type of analyses for the apple falling from the tree. We could take an average value going from the start to the finish, and sorry, that's not a straight line, but it should be. And you can take any one of these points, for example, take this point, and try to balance a line using a ruler on it, and then you can find the slope of this line. And so maybe I'm going from this point over to this point, and you can draw a slope triangle and calculate your rise over your run. And that would be for this point right here. Our slope of this would give us our velocity at that point. Now, if you take a look at these 13 questions, you will find that we've answered every single one of these questions, or we've come close to this, and you can figure out all the answers on your own. So what you need to do is read each one of these questions, go back to what we did on the worksheet, and you should be able to figure out the correct answer for each one of these. Good luck.